So let's kind of get everyone up to speed and awake. What's that? Yeah, I thought I put you in airplane mode. 1 second. It's Octane something. Cool, we did it. We got Octane something. Yes, Octane. All right. So, what are the somethings? Propoxy. Propoxy. If I do the same thing you just did. Methoxy. Chloro. And we're going to pretend that we're going to put this up top just so it all fits. We're going to pretend it's all in one nice line. Bromo. I still can't do it. Bromo. Chloro. There you go. So, which way am I going to number? Am I going to number orange or am I going to number blue? Well, if I go blue, what's my lowest number? If I go orange, what's my lowest number? So, which way am I going to go? Orange. I didn't mean to make you sound so defeated. Orange. All right. So 3. Let's get all these. 4, 5, 3. Oops. 4. And then... No, try again. He's good at this, he swears. 5 bromo. There we go. 4 chloro. 3 methoxy. 5 propoxy. Reasonable? Let's do one more for good measure here. All right. It's a little ugly, but whatever. I would say it's what's on the inside that counts, but there's nothing on the inside of that. Soulless. All right, so what is this? As he erases your H. There you go. Van Hook also watched the syllabus video, and I think he thinks all the videos I have on YouTube are that well produced. I don't have the heart to tell him that no, I don't spend that much time on all of them. Though Ace Ventura made it in the last lecture if you go watch that video. Heptanol. What kind of heptanol? Yep. Cycloheptan. Oh, we don't have to use a number because we know when we number, the alcohol is number 1. Right? Then we have chloro. And then what's the other group? F-oxy. So do I need to number counterclockwise or clockwise? Clockwise, because that gives me 3 as my next number. So it'll be 3, 5. As opposed to 1, 2, 3. Opposed to 4, 6. So we'll go clockwise. So that'll be 3 chloro, 5 ethoxy, cycloheptanol. Seem good? So I kind of cheat on this next one, right? So here is, you gotta look. There's only one out of all of, there's only one like legit true ether in this whole molecule, really, which is right there. But it does fall in the category of ether containing antibiotic. So this is used to treat C. diff, and it inhibits bacterial RNA polymerase. So again, this is another molecule that I'm sure is something that we get out of a broth that one bacteria uses to murder another bacteria. So we just grow up big vats of the bacteria that make this, and then we skim this off the top. All right. So next up, we're going to talk about amines. Right? So again, you remove an H from a hydrocarbon. And you add, and we're going to say NH2, but we'll get to that. It kind of can change. So if you have an NH2 here, this can be an amine. You can start removing hydrogens from the nitrogen and adding carbons, and they still count as amines. So this is an amine where one of those hydrogens becomes a carbon, and this, like that, is an amine. So all of these are an amine, right? Each of them is an amine. So we categorize amines, primary, secondary, tertiary, but the way we categorize amines is completely and totally different from how we categorize hydrogens, halides, and alcohols, because nothing's easy. All right, so primary, secondary, tertiary amines count the number of carbons bonded to the nitrogen. So this nitrogen has one carbon bonded to it. So this nitrogen is a primary, this is a primary amine, right? It doesn't matter if that carbon bonded to the nitrogen is primary, secondary, or tertiary. It just matters how many carbons are on that nitrogen, right? This nitrogen is on a secondary carbon, but it's only bonded to one carbon. This is still a primary amine. If you have two carbons on your nitrogen, it's secondary. So again, it doesn't matter. They can both be, sure. Sure, no problem. So it doesn't matter if the two groups on the nitrogen are, let's say, both methyl groups. It just matters that there are two there. This amine is a secondary amine. So it's a different way of doing primary, secondary, tertiary than we did before. It doesn't matter what carbon's attached to, it just matters the number. And this is a tertiary amine. Easy enough? So we can do the same thing with the formal charges that we did on oxygen, we can do with nitrogen. Right, where instead of actually doing the formal charge formula, we can just kind of count and cheat, right? So for formal charges, see if it'll fit. Yeah. right? So if you have an N with 3 bonds and 1 lone pair, right, you're going to have no charge. This is the most common way you see nitrogen, is what we were drawing before, where you have just 3 bonds to your nitrogen. And it doesn't matter if those are the carbons or if they're double bonds involved, as long as you have 3 bonds to your nitrogen, that nitrogen is going to have no charge. Just like oxygen, if you go up your number of bonds, you're going to go up in charge. So if I add a bond, if I go from 3 bonds to 4 bonds, right, you're going to have a +1 charge. Right, so, and you're going to have no lone pair, because that lone pair is going to get used for something, used for the bond. So here, I have lone pairs on each of these. Right, in this, I have no lone pairs. I have 4 bonds to my nitrogen. It ends up having a positive charge. It can be an additional carbon-nitrogen bond. You could end up with extra hydrogens on your molecule and have a positive charge. But going up a bond, going to your 4th bond to nitrogen, is going to give you a positive charge. Right? If you have a nitrogen with 2 bonds, you're going to have 2 lone pairs. And it's going to give you a -1 charge. Right? You take off a bond, minus charge. So, right, now you have NH, and you have a negative charge on your nitrogen. Where you could have 2 carbons and a negative charge on your nitrogen. Right? You still have 2 lone pairs. So if I were to draw out the lone pairs, like that. But again, remember, we kind of treat, when you see a negative charge, just think of it as that's a lone pair. That's an extra lone pair that the molecule has, so that's what's giving it a negative charge. So if we don't draw out the electrons, just assume the 2 extra electrons are on that negative charge. So naming for amines is perhaps the most straightforward in terms of the suffix of all of the suffixes. Right? So naming amines. Right? So you remove the E from the end of the hydrocarbon. And add, brace yourself, amine. So when you have an amine, you put amine at the end of the name. You're 100% not allowed to forget that one. That one's just low-hanging fruit. So after you have the suffix, all the things that we did from when we named alcohols in terms of how you number and whatnot, that is going to stay the same for amine. So you want the amine suffix to have the lowest possible number, is really the important one. Now, the thing that is odd here is groups on the nitrogen get an N. This is supposed to be in italics, but I don't have that setting on my stylus here. Get an italic. Oops. N, to denote that they're on the nitrogen and not on the chain. And I will show you what I mean here in a second. It's just easier to show you than to, write it, but we'll write it first. All right, good for me to switch and do some examples. I'm going to just go say yes and just go forward. All right, so the easiest stuff is something like so what would this be? Hexane what? Hexanamine. Just like with the alcohol, I need to leave a space for the number. And then what substituent do we have? Methyl. So we have methyl, hexanamine. Do I number orange or do I number blue? Blue. Be 2-amine, 5-methyl. Actually, make that a number. There we go. 5-methyl. Pretty straightforward. So, like, primary amines are the easiest ones to name. So let's say we had so what would this be? Cyclobutaneamine. There's an E on the end, I swear. And again, since it's on a ring and it's our only functional group, we know we're going to start numbering at the amine. So what are my other groups? Agreed. Indeed. So numbers? Three, two, two. Yep. So far, so good. That's easy enough, right? Now for that whole italicized N thing that I brought up. So right now, let's say we have a secondary amine. All right. I still have hexane amine, right? That's still the same. Right. And I have a methyl group as hanging off of the molecule, right? It's not, I have this carbon here that's not part of the longest chain, so I need to denote it somehow. So that's still a methyl group, right? But that methyl group is not coming off of the longest chain, is actually attached to the nitrogen. So that's where I say I put an N. So this N is saying that the methyl group is coming off of the nitrogen that we named with the amine suffix. So this will be 3. So it's N-methylhexanamine. So the N is just telling you this is on the nitrogen. It's not coming off of the longest chain. Next step. Do this way. So what would this be? It would. So it's diethyl butanamine. Nitrogen's on carbon 2. both ethyl groups are coming off of the nitrogen, right? We still have the same like numbering rules that we would have with any other dye, right? I have to have two numbers because I have two substituents. In this case, it's NN because they both come off of the nitrogen. So it's NN diethyl butane 2-amine. So we have something like this, right? Pentane amine, letters are hard. Amine, right? And then it's ethyl, methyl, right? So we still do this, we're going to number in this direction, right? So it's going to be N-ethyl, 2-methyl, 3-amine. So far, so good. So like one other little variation I want to show you. And we should be... Yes. So basically, you're treating the N like it's a number, which is super weird to say, right? But it is what is denoting where the substituent is in the molecule. So it kind of is filling the same role that like the numbers fill. So you kind of treat it like it's a number and you still put a dash there. Just the other thing I wanted to show you, we'll do a simple one. Is if you have, right, if you have the N and then the group on the nitrogen and a group on the main chain are the same substituent. So this is dimethyl propane 2-amine, right? The N comes first when you're listing the numbers, right? So it's N, 2, dimethylpropanamine. Because you always, I guess I haven't formally said this, you always list the numbers in like increasing order from the smallest number to the largest number when you're listing, like if it's 2, 3, 4 trimethyl, you always list it 2, then 3, then 4. N is the least numbery number. So it is the smallest number because it's the least number. So it comes first. So far, so good? So this, before the last slide, is where I ask the big question. If, per se, your first exam was, I don't know, 40% naming, how do you think you'll do? So I need you to turn that to like at least medium paced to good. If this was a written exam, I would tell you that you have to be super fast. It's going to be a little bit different because it's going to be all on the Moodles, but you do need to be quick just because you are going to have a lot of them. So that's just my... On a written exam, usually I will have somewhere between 30 and 40 points will be naming, and they will be... Usually on the first exam, naming will be 3 points a name. So I will do usually maybe 8 to 10 that are, here's a structure, what's the name? And then like 4, here's the name, what's the structure? Yeah. So, after your big talk about being tech savvy, basically what I end up doing is basically your exam is going to be like multiple choice and matching. Yeah, I'm sorry, it's just awful. Because I can't expect you guys to like have to draw stuff, and like I really don't want to sit at a computer for like 15 or 20 hours grading a bunch of like cell phone pictures of things that you drew like on like paper. So I'm going to basically, there's going to be like a bunch of options for names. I'm going to try to get creative with how I can like ask questions, but it is going to basically be all like some sort of multiple choice matching. So you're not going to have to draw anything on the exam because I don't know how to make it so you have to draw something. Like, I don't know how to, like, enable that on Moodle. So, you know, it'll be something like, let's say, 2-ethyl, no, can't do 2-ethyl. I can. 2-ethyl, 3-methyl, cyclohexane, amine, right? So if I give you the name, right, and then give you like a collection of structures, right, you should be able to pick out the right one. But I'm just going to draw the right one, right? But you should be able to draw the structure from the name, right? We spend most of our time in class going from structure to name. If you can do that, if I give you the name, you should be able to like reconstruct the structure from the name. And that's like the whole point of the systematic nomenclature, is that anyone who looks at this name, if I spelled methyl correctly, right, should be able to draw the structure and go like, oh, the parent hydrocarbon is cyclohexane. There's an amine on it. Okay, I'm starting number at 1. Then the next, on carbon 2, there's an ethyl, so I go over a carbon and draw an ethyl. Carbon 3, there's a methyl, and then you get the structure that way. Now, before you ask, right, let's say you drew it like this. It's still the exact same thing, right? Right, all the groups are in the same relative position, so it still has the exact same name. So it's not that you have to draw it in the exact same orientation that I do, because that orientation doesn't really matter. Does that make sense? All right, so this is actually the last slide for the first set of slides. And this is a sulfonamide antibiotic, right? And this is kind of one of the first classes of antibiotics. It's, so this is a sulfonamide, this part of it here, right? Technically, this is my amine, right there. Right. So, story time, settle in. This is why I have trust issues, undergrads. So, when I was in grad school, all the graduate students taught the labs. And so we had 3 like multi-step synthesis things that organic 2 students could do. You could like pick like, okay, you do this synthesis, you do this, and they would spend 2 or 3 weeks making a molecule over with multiple steps. And so there was one where you made a sulfonamide antibiotic, and you used something called chlorosulfonic acid. And chlorosulfonic acid reacts violently with water. And so the guy in the lab beside me picked his best student and was like, all right, here's what you need to do. You need to pour this chlorosulfonic acid into a graduated cylinder. Do not use a funnel. Do not wash anything with water before you measure this out, because if you do, it will be a bad time. So his student heard him say, do not use a funnel, do not wash stuff with water, and went, so I should wash a funnel with water and then use that to measure my stuff. So that is what his student did. He made sure to dry it, paper towel, but there was enough residual water on the funnel that when he poured the chlorosulfonic acid, it exploded. And it hit his lab coat and burnt through 3 layers of clothes before we could, like, hose him down. So, this is why I have trust issues. Because it's like, don't do this. And you guys were like, so I should do that. No. Do you like your fingers? Most days. Then don't do that. Oh, no, I'm going to do it. So, yeah, so I'm still traumatized. Like, I've never had to put anyone in the shower. We've come close. Never had to do it. I don't want to start now. All right. So, we're going to transition to the second set of slides after story time. Again, all of my stories end up with someone almost getting named, but not quite. Right? So, we're going to talk about conformations of alkanes. Right? Right, so basically what this really goes to is a compound can have different spatial arrangements. Right, of the atoms due to rotation around single bonds. Right. So a molecule could have the exact same name but look slightly different because of how the atoms are arranged, due to the fact that single bonds, carbon-carbon and carbon-oxygen single bonds, are free to rotate around the bond. Right? So, these different looking compounds are called conformations. Right? I'm going to show you an example here in a second. Right? So I'm going to click over. That is butane, right? No problem, super easy. Now, if I were to rotate around that, this is the Wakefield twist arrow, patent pending, right? Whenever I draw a little like squiggly arrow, it means I'm trying to show you that something's rotating, right? So if I rotate around this bond, I can end up where instead of the 2 methyl groups being on opposite sides of each other, they're on the same side. But it's still 4 carbons. So it is still, what's it called? It is still butane, right? I haven't changed the molecule. I haven't changed how the atoms are put together. I've just changed how they are arranged in space, right? So different conformations are called conformational isomers or conformers. So this version of butane and this version of butane are just conformers. Right? They have the exact same name. They have the same constitution, right? The way the atoms are put together are the same, but the way they are arranged is slightly different. All right, we're gonna do something. One conformation of Wakefield, touchdown Wakefield. Other conformation of Wakefield, I don't know, half a swastika, which is too much swastika. Right? right? Both of them still Wakefield, but in different conformations. Still Wakefield. Right? That's all the molecule's doing, is just moving around, like slightly debasing itself and becoming less and less respectable as he does it. But still, me doing a very bad robot is just me changing conformations. Back to sharing where it's safe and you guys can't really see me. Back to my safe little white screen where I'm just a little corner now. Alright, so there are three main ways that we can draw conformers. All right. There is the wedge dash method. Where, okay, let's say we have, let's go with butane first. So I'm going to draw butane. So the wedge dash method is to say, all right, this hydrogen here is on a wedge. It's sticking out at me. This hydrogen here is on a dash. It's pointing away from me. Next carbon, this hydrogen is on a wedge. This is on a dash. So remember, wedges, dark bonds are out/up. This is pointing out of the screen or up from your page, right? And then dashes are in/down, right? So a dash is pointing into your screen or down away from you on the page. All right, so this is the wedge dash way of drawing them, right? The next way to do this is called the sawhorse method. I wish I could get these on the same page. Right, so, sawhorse. Right, so the sawhorse is we take the wedge dash and we kind of turn it at an angle. Right, so we've turned it. So instead of looking at it in profile, like in a straight profile, we've kind of tilted our perspective. So we don't have to use wedges and dashes anymore because we can draw the hydrogens to show which ones are on one side of the bond and which ones are on the other. Right, so in the sawhorse, right, or sorry, in the wedge dash, these two hydrogens that were both on a wedge, they're on the same side of this bond, right? And these two that are on the dash are on the opposite side. But you can see that, right? These two hydrogens are pointing towards you in the sawhorse, just like these two hydrogens are pointing out at you in the wedge dash. These two are pointing away from you, right? They're on the other side, the far side of the molecule. And these two here are pointing away from you. They're on the far side of the molecule from you, right? So the sawhorse, you've given the drawing a little bit more perspective, a little bit more depth. So you don't have to use the wedges and dashes because you can see, based on how it's drawn, which hydrogen's on one side of the molecule and which hydrogen's on the other. Everyone see that? That makes sense? No one's saying no. So now the last way to do this, absolutely. She just like baited me. She's like, I'll wait for him to change the slide, then I'll get him. No problem. All right. The last way to do this is Newman projections. And this is the kind of the next progression. So, there you go, holding stuff up. If this is wedge dash, where you're looking at it fully in profile. Sawhorse is where you're kind of looking at it at an angle. Newman projections, you're looking at the molecule down the middle bond. Right? So, again, if we have, I'm going to draw the sawhorse projection here. So if it looks like this in the sawhorse, right, this is what we just had. The Newman projection, this is where you're going to hate my drawing, put little eyelashes on it. This is an eyeball, right? You are looking at it right down that bond. That's the Newman projection. So what you end up seeing is this right here is effectively this carbon. That carbon has a methyl, a hydrogen, and a hydrogen on it, right? And that's this carbon right here. This carbon behind it, you can't actually see that carbon. You just see the things that are coming off of it. So you see a methyl, a hydrogen, and a hydrogen. All right, so what I always use is if I can find a good example. Perfect. Thank you, Internet. So you know that Indian dance style where like one girl lines up and then like there are like a bunch of girls behind her and you just see arms, right? You see one girl and then she looks like she has like 10 arms, right? That's what you're getting here. You're seeing that front carbon. That's the front girl, right? The carbon behind that front carbon, you don't get to see that it's there. It's blocked out. But what you do see is you see the fact that that it has groups coming off of it. So let's see here. Right? So something like this, right? Where you see the front person and then you see the arms coming out. That's the Newman projection. You see the front carbon and you see the groups coming off of it in the back, but you don't actually see what is attached to those arms or attached to those groups. It's blocked out by the front. That make sense? Okay. So we go from wedge dash, which is like hard profile, right? 100% you're looking at it from the side, to sawhorse where you kind of have an angled look at the molecule, to Newman projection where you're looking straight down the carbon-carbon bond. And we're going to spend most of our time doing Newman projections. So there are a bunch of different conformations that a simple alkane can be in. And we're going to kind of work through those, but we're going to start at the simplest thing possible, which is ethane. So we're going to do the conformations of ethane. Right, so you know ethane, right? It's just a line. If we draw the hydrogens on it, right, we got a bunch of hydrogens going on here. Right? And there are two conformations for ethane. So if I draw the Newman projection, right, if I look at the molecule that way, like so down this carbon, that front carbon, my circle gets uglier and uglier. My front carbon is going to have three things on it, right? It's going to have, that you can see, a hydrogen, and a hydrogen, right? Now, I can't see this bond, right? That bond is the one I'm looking straight at. So I can't see it, but I can see the carbons that are coming off of the hydrogen back here. The carbon back here. And that's going to give me, you're going to see a hydrogen, and a hydrogen. So you notice when I draw these, the groups that are coming off the front carbon, this, we'll make it blue, this blue carbon here, right? They go all the way to the center of that front circle, right? So they clearly look like they're bonded together. The groups that are at the back, that are on the green carbon, pick another color here, purple, right? These hydrogens here, you see them, their bond goes to the edge of this circle and stops, right? Because you can't see their bond go all the way back to the carbon they're bonded to, right? Just like you can't see, like, you know, the girl's shoulders, like their arms come down and they kind of stop. You don't see them make the bond to the body. You also don't get to see the hydrogen make the bond to the carbon. You just see part of the bond and then it stops. So you always kind of draw the bonds in the back to stop when they get to the circle. So this conformation of ethane is called staggered, right? Because the hydrogens alternate. There's the hydrogen from the back carbon, and then if you go clockwise, right, then you have the hydrogen from the front carbon is next. And then back carbon, front carbon, back carbon, front carbon. They're staggered as you go around the ring, or around the diagram. The other conformation for, I'm going to erase this for a second. It's still staggered, I promise. The other conformation is, let's say I grabbed this hydrogen here and rotated it. If I grab that hydrogen and twist it, all these other hydrogens are still attached to the same carbon, so they're going to rotate as well. That's where we get the little twisty arrow. Right? This is staggered. Right? This is going to be called eclipse, because now my hydrogens are, I put it in the wrong spot. My hydrogens are on top of each other. Right? I draw them just off to the side. Did a bad job here. Right? Just slightly off. Because it wouldn't make any sense to draw them right on top of each other because it'd be hard to see. So when you draw the eclipse conformation, you put the hydrogens really close together so that it shows that they're on top of each other, but you don't draw them right on top of each other.